In today's video, we will go over direct and inverse proportions, both algebraically and graphically. Welcome back to my channel, Numerics with Nadia, and let's get into our lesson for today. So this topic came from one of you guys. Thank you so much for commenting this question, and I hope this lesson helps you. Let's get into our learning objectives for today. By the end of this lesson, you guys should be able to define direct and inverse proportions, represent both relationships algebraically, interpret and compare graphs of both relationships, and then solve some real-world and numerical problems involving proportionality. Now that we've gone through our lesson objectives, let's get into part one of our lesson. We are first going to start off with our definitions. So we have two types of proportions in our lesson today. We have direct proportions and inverse proportions. Direct proportions are two quantities that increase or decrease together at the same time. So they're either both increasing or they're both decreasing. For an inverse proportion, one quality increases as the other decreases. So their product is a constant. That means that they're opposite, right? So if one's increasing, the other is decreasing, or if one is decreasing, the other is increasing. So that's our definition. And now let's get into the algebraic representation, right? Like, what does this look like? I put them side by side so we'll be able to compare and contrast. For a direct proportion, the algebraic form is y equals k times x. K here is the constant of proportionality. And the key characteristics of a direct proportion is that it's a linear relationship. It passes through the origin, 0, 0. And as x increases, y increases proportionally. Also, as x decreases, y would decrease proportionally. Now, for inverse proportions, the algebraic form is y equals k divided by x. K is the same, it's the constant of proportionality. But what are the key characteristics of an inverse proportion? They are that it's a nonlinear relationship. For what it looks like, the graph forms a hyperbola. And then, as we know, for inverse proportions, it's opposite, right? So as x increases, y decreases, and vice versa. And the product, x times y equals k, remains constant. So those are the characteristics for inverse proportions. And we also went through the characteristics of direct proportions. And now that we know what it looks like algebraically, let's go ahead and see what the graphs look like. So we have two examples here, one example of a direct proportion graph and one example of an inverse proportion graph. The graph of the direct proportion is up on the right, the line is red, and the equation of the line is y equals 2x. And here we can see that it passes through the characteristics, right? We remember that the key characteristics of a direct proportion graph are that it is a linear relationship and it passes through the origin. And we can see here that as x increases, y increases. So they both go in the same direction. So that top graph would be a direct proportion graph. And now for the bottom one, our equation is y equals 10 over x. That follows the same algebraic form. And we can see here that the relationship is nonlinear. It forms a hyperbola. And as x increases, y decreases here. So that's opposite. So that meets the criteria of a inverse proportion graph. Now that we've gone through the graphical representations of direct and inverse proportions, now we'll get into some examples. So for our first example, this is going to be a direct proportion. And it's saying if y equals 12 when x equals 3, find y when x equals 5. So the key thing here is we have to find our constant of proportionality, which is k. And since it's a direct proportion, we know that y equals k times x. So in knowing that, we can kind of substitute in. But first, before we do that, let's solve for k. So since we're solving for k, we can divide by x on both sides. And then we isolate k, so k equals y divided by x. Now we know our y value is 12 because we're given that y equals 12. And our x value is 3. I'm going to underline where I'm getting that from the instructions right now. So we know that k equals 12 divided by 3. We know 12 divided by 3 is just 4, right? So now we can go through and find what y would be when x equals 5, now that we have calculated our k value. So we know that k equals 4, so we would do y equals 4 times 5, right? Just substituting in for k and substituting in for the x value we're looking for. And we know that 4 times 5 just gives us 20. So that would be our y value. And just to prove and show that this is a direct proportion, let's just do a quick little xy table to compare our values. So we started with x being 3 and y being 12. And then we were given that x equals 5, and we just calculated that when x is 5, y would be 20. So we've seen that x goes from 3 to 5, so x is increasing, and y went from 12 to 20, so y is also increasing. So that would make this a direct proportion. I highly recommend you guys do this on the little side of your paper if there's a quiz or something going on, just to ensure you did everything correctly. Now we'll move on to our second example. Our second example is an inverse proportion, and we are asked if y equals 4 when x equals 5, find y when x equals 10. So again here we know that for inverse proportions, y equals k over x. When you go through and you solve for k, you see that k equals x times y. And here we're given that x is 5 and y is 4, so we would just do 4 times 5, and that gives us 20. So we know now that k equals 20, and now if we're looking for y, we know that y equals k over x, so we can substitute in for 20, and we know our x value. So we would just do y equals 20 divided by 10. That gives us a y value of 2. And again here, let's do a little xy chart just to make sure that our math lines up with this being an inverse proportion. So we started off with x being 5 and y being 4. Our x went up, so it increased from 5 to 10, but our y decreased. So that would be opposite, and that would make this an inverse proportion. So that wraps up our practice problems for today, but I just wanted to show you guys this has a lot of real-world applications. So let's go through a few examples of direct proportion applications in the real world. One would be the distance formula. 2, you have the cost formula, and anything like the more hours you work, the more you will earn. And now for inverse proportions, the more number of workers you have, for example, the less time it would take to finish a job. So that would be an inverse relationship. Then you have pressure times volume, Boyle's law, and also speed versus time. So those are a few examples of the real world applications. I hope you guys enjoyed this video. Please feel free to comment any questions down below. I'll do a whole video on it for you guys, as you guys saw for this lesson. Feel free to like the video if you enjoyed it, subscribe if you haven't already, and share this video with a friend, and I will see you guys next time.